Hello, good morning. I think I'm online. I hope I'm online. There are people, yeah, there's people in the chat. Great. Hello, everybody. Apologies for the few minutes of delay. I did not watch my time. Happens. Good morning. I know this is not actually the greatest day to spend your morning in a class. I've been watching the news, as everybody can imagine, and I guess everybody else has been doing so too. And if you much rather hypnotize the pulse, you're welcome to do so. This stream will end up on Twitch, and again, all the streams will eventually land on YouTube. I'm aware that today might be a tricky day for some people to attend. Once again, I am still waking up. It's 8 o'clock in the morning here, and yeah, I mentioned before 8 o'clock is not my favorite time of the day. Whatever, though, I'm weaponized. I weaponed up with my giant cup of coffee. And I'll take little tiny breaks to keep sipping that coffee throughout the class. What are we going to do today? Much more important, what have we done the last couple classes? So by now, you all should have heard about the different registers that we can find in an x64 Intel platform. Not all of them, the most important ones. You should have heard about how function stack works. You should have recognized how functions look like in a binary. You should know what an import table is. You might remember what an export table is. You should more or less know how to handle either pro and the different navigation tricks that we can use inside the tool. And as I'm saying all of this, I don't actually expect you to know all of this, but you should have heard about it. And as we keep going through binaries today, and as we keep navigating the tools that we have, I hope that you get the feel of what we're actually doing. Once again, you cannot learn reverse engineering from a slide deck. You cannot learn it from a book. You need to do it. And this is what we're going to do today. Okay. Let me just quickly get things set up here. Then, what I wanted to start off with today to make it nice and smooth for everybody is finish with the slide decks, and that's going to be quick. It's going to be very quick. Let's have a quick look. Instructions. Yeah, let's take off here. So I have OCD big time, and going through a slide deck halfway just hurts my feelings. So this is why we're here today. All right, let's jump right in. So the past couple classes, you saw instructions, right? And lots of instructions are self-explanatory. Like if you look at an AND instruction, that is a logical AND. If you don't know what a logical AND is, this is easily Googled. And again, if either of these instructions are unclear, like I guess about half of them are not as self-explanatory as one would wish, then please use either the Intel manual for the big stack of information or Google them. Once again, a search engine is the best reverse engineering tool that you can imagine. And something that is not as obvious as I'm speaking is that sometimes you can also look for combinations of instructions. So if you look at a push and a call instruction in a binary and say you're not aware of how a function is called in a binary, then you can totally throw those into Google and see what comes out. I can't guarantee you that the explanation comes out, but I've seen it, especially with curious instruction combinations. Like last time when we were looking at the division and we saw the CDG, and sometimes looking at one instruction and looking at the explanation for one instruction doesn't actually help you much, especially if you don't understand the others either. But lots of times such instructions come in like combinations in patterns, and oftentimes the whole pattern is explained somewhere in in like the full picture. Believe it or not, there's other people out there reverse engineering, and they often run into very similar problems as we do. So there is a Stack Overflow for reverse engineers, whatever it's called right now, I can't remember. But um, if you type in a reverse engineering question into Google, these particular sites pop up. There's a Reddit for it too, and very often people have had similar problems before, and these problems tend to be explained on such websites. That makes life as a teacher a lot easier. Just as a quick overview, there's data transfer instructions, like these groups I made up. There is no official documentation that says, that talks about data transfer instructions. Why is this bar up there popping up? But that would be like the moves and the pushes and the pops and the exchange and all these instructions. Then we have logical instructions like logical and, logical or, logical XOR. We have arithmetic instructions like add, sub, compare, divide, and multiply, and all of these. And some of the most important ones is like this group of control transfer, which is something that we're going to be looking at on the next couple of slides. This is something very important to watch out for in the binary, because it can tell us very quickly about how, like, it can very quickly give us an idea of what a certain function wants to do. Control transfer often enough happens with call instructions. We've seen a lot of those before. But there's also the jump instructions and loop and leave and ret. And these pretty much give us the structure of a function, and later on, eventually, the structure of the whole binary. And that is just very important for us. And of course, there's other instructions. In fact, there is, I don't know how many, like thousands of instructions on the modern Intel platform and on, frankly, most other platforms as well. So like instruction sets nowadays are very big. And yeah, what's interesting about them is they're mostly implemented in hardware. So like if you issue an add instruction on Intel, the CPU knows that add receives two components, and the CPU knows that these need to be added and stashed somewhere. So that is all up in the that's all up for the tiny little fairies that live in the CPU, and they do this job for us. In the other instructions, what is interesting for us right now would be the LEA instruction. We quickly talked about this in the last class. Like LEA means load effective address, and that's a little misleading because the operand, like the result of the LEA instruction, doesn't necessarily need to be an address. What LEA does is it performs an addition, like an arithmetic. So originally, I think it was designed for taking an address and adding an offset. So you have an LEA instruction, and then in edgy brackets, you see address plus offset, and the result of the LEA is this sum of address plus offset. Right, but again, this can be used for addition of constants and regular numeric values as well, so it's not limited to addresses. Okay, the others are cosmetics. I mean, don't get me wrong, they're all very important, but not for us right now. Jump variations. This is important. Let's just quickly swoop through these. Everything that starts with a J is a jump. That is true. And the letters that come after the J describe the nature of the jump. Like, for example, jump equal is taken if two values result as equal, and the right corner, the right column of the slide where it says flag conditions describes what it means for the CPU that two values are equal. As you can imagine, the CPU is not a person, but needs numbers to evaluate things. And in this case, the numbers, like the values of the flags in the effects register, serve the CPU for decision making. We talked about the e-flags before in the very first class. You remember there's a bunch of flags in there, and these flags, direct the control flow in our binary. They do other stuff too, like control flow decisions aren't the only purpose of the e-flags, but one very important one. Most important in this form of decision making is the zero flag. That's the one I remember the best. And then there's the others, the carry flag and overflow flag and whatever other flags. You see in my lack of enthusiasm for the e-flags that as a reverse engineer, like me, I can't speak for everybody else, but I personally, I don't pay so much attention to the e-flags register and the different flags that are set there, because usually the purpose of a jump can be derived from the code flow, from the logic. And dealing with the flag conditions of a jump instruction can sometimes be very, very confusing. As you've seen before, like we talked about this briefly with the compare instruction that followed a conditional jump. The conditional jump that followed the compare instruction. The zero flag is set if the result of an arithmetic is zero, is one. Sorry, no, the result is zero, the zero flag is set one. Yeah, you see the confusion that can already arise from that. So if this flag is set, the result was zero, hence the like a jump equal for instruction would be taken. It gets especially interesting when there's more than one flag involved, and then yeah, your best choice is pen and paper and sitting there and evaluating these different flags. That's usually what you do if you have to be really, really sure that your analysis of a given branch and your analysis of the code flow is 100% correct. You do that quite often. If you identify the module that is particularly interesting to you, and I like to bring up the example of ransomwares because they're so simple. If you're inside of ransomware and you want to figure out the encryption that is being used, and you need to figure out each and every bit that this algorithm processes, then you will sit there for a long time and need to figure out how exactly all these different branches in the algorithm are taken. Generally speaking, then, you'll see that later on when we look at the SQLite 3 DLL. If you look at a very large binary with very large functions and like the complex call graph, you typically don't go analyzing each and every instruction, especially not each and every conditional jump. And then it's good to work with, how to say, logic conclusions. Yeah, you'll see that later on when we look at actual code. And what's especially upsetting is there isn't only regular jump instructions, but there is the negated form of the same jump instruction as well. So for the jump equal, for example, we have the jump not equal. For the jump greater, we have the jump not greater. And these expect, in most cases, the exact inverse pattern of flags, but not in every case. So yeah, it's just really, really upsettingly confusing. But don't worry, we got this. Just keep the jump instructions in mind. Finally, the last chapter of the slides, and I promise you we get back to the binaries in a second, the control flow. The control flow in the binary, gives us an idea about the structure. Haha, yeah, the structure. The control flow divides up modules and patterns of functionality. So like the most basic unit in the binary is an instruction. The next most basic unit in the binary is a basic block. Every block you see on this graphic here is a basic block. The next unit would be a function. So a function is separated into basic blocks, and basic blocks contain instructions. The reason why basic blocks are so important for us is because they can be displayed in a graph, which is the graph display, the graph window in IDA Pro. So what modern disassembly frameworks do including Ghidra and including Radar 2, is they can display functions in their graph representation. That makes reverse engineering them so much easier. Imagine like a large function where you don't know where's up and where's down and where's the important part and where's the unimportant part. You look at it in the text view and you see like thousands of instructions in front of you as a list, as a text. Theoretically, as a seasoned reverse engineer, you should be able to work on that too. Like, it's not impossible. It's just so much nicer to look at the graph and go basic block by basic block and know, like, in one with one view, like where the basic blocks are. And what's more, in such graphs, we can see at one view, like where the branches are, where the loops are, and where the switch case statements are at. And this is something like a visual graph experience that we're gonna do right now. Like if you look at that graph in front of us, I neatly already marked the important parts. There is a bunch of branches in there. Why are branches important? Branches are a way of decision making. So if you see a branch, before the branch, something happens that causes this decision to be made. So we can assume that with just one glance that this first busy block here contains a compare or something that uh, yeah, something that interacts with the efflex register, to be precise, and that based on whatever this compare, this decision results, we either jump directly to exit. You see this red branch that goes all the way around. There's another block down here, and then we're at the exit block at the bottom. On the other hand, if this decision is not taken, we go to the actual body of the function, which is over here. Looking at those conditions can tell us very quickly about exit conditions. Like if you enter a function and you see like a big staircase, so to say, of lots of conditions that all lead to the exit branch, you can see that some input is evaluated, like most likely some input is being evaluated throughout this staircase. And if you look at a function like the one we have in front of us, you see this big blue arrow that wraps around most of the code that we have in this function. That is a loop. Red arrows are negative branches, like negative decision, like branches that are taken after negative decisions. Then we have green arrows that are branches being taken after positive decisions. And then we have blue arrows, which are taken in any case. So this tiny little blue arrow here will always be taken because there is no other option to get out of this basic block. Right, and that's true for all the other blue arrows as well. They all are final. And yeah, if we look right here, the loop looks very big, but I can tell you it's actually not that huge of a loop. I wonder, we'll be looking at that in the disassembler in a bit, and then we can analyze what happens in the loop. Last but not least, though, there's the switch tag down here, and this is what a switch statement looks like approximately, like in the graph. If you look at a large function graph and you see like this kind of pattern in there, you can assume that there is a switch case happening, and that usually also means that some form of input is evaluated or some value needs to be evaluated. And that is very interesting for us because each and every of these boxes that follow the actual switch is that, like, in each of these boxes, something interesting is happening, or very likely something interesting is happening. And then we can just go and look at like which condition is evaluated by the switch statement and what are the different cases based on the decision. So you see, just looking at the graph, there is a lot of different points that could be interesting for us to start analysis with. And essentially, in the end, when you look at a real binary with real big functions, you don't go reading each and every instruction. Again, you look for interesting parts and start reverse engineering there. And the challenge in this is to find the interesting spots first. Now, this is a very simple exercise binary. There isn't much going into this function, and there isn't much coming out of this function. You see in the SQLite DLL that that is very unlikely the case if you look at a bigger binary. Like, there is an entry point somewhere, and from there it starts, and then there's a rabbit hole of dozens of functions that call each other and like have more or less complex bodies. And that is just because very simple source code can become very complex inside of the binary very quickly. So yeah, brace yourselves. Finally, a picture show. These are the last 3 slides in this presentation, I believe. Branches can have different looks to them too, but the branch is typically identified by this red and this green arrow. And yeah, they help us analyze the decision-making process. If you want, you can spend your homework time with looking at these pieces of source code and reading through the assembly on the right side. That might be very instructive. Now we have a switch cases I just mentioned, which in most cases, not all, but in most cases results in these parallel boxes in the graph, in the upper graph. And then we have loops, which again are usually identified by arrows, fed arrows. The arrow doesn't always have to be blue. Sometimes it's green, sometimes it's red, based on whether this last box down here makes a decision. By the way, what's interesting about loops is sometimes you have exit conditions. So you're in the loop. There's something happening in the beginning of the loop. There's something happening at the end of the loop. And usually there's something happening in the middle of the loop. And then there might be this exit condition. Usually there's a lot of those, but yeah, for simplicity. And for us as analysts, what's interesting about loop is to see what makes it tick, like what makes it go around, which values come in, and based on what do we keep on looping? So based on which value or decision do we take this branch over the exit branch? Like, why do we keep going? And the second thing we're interested in is what is happening in the loop body. That would be right here. You see the move, add, move, jump. So these moves and adds, that's most likely what's interesting for us as analysts. This much about loops. This is a very simple loop here. There's bigger ones, but yeah, this is typically how we go about loops. Okay, that was the slide deck. Let's go back to our disassembler. Main. And click. Awesome. Here we are. Is there any questions? How does IDA know that these basic blocks are part of the switch? How does it know what goes into Rex to make the jump? Good question. Yeah, basic blocks are identified through a disassembly framework, which is why we pay so many thousands of dollars for an IDA Pro license, frankly. Let's jump into the specific function and talk more about the basic blocks. So typically how function detection works, and function detection is one of the most important things, like in my opinion, in a disassembly framework, because it helps us start and end the defined pieces of code. By the way, this graph view for IDA Pro is only possible if a function is being detected. And we talked the last time a bit about how function detection works. It mainly relies on the stack pointer. Like the stack pointer needs to be balanced. RSP is the one register that cannot be out of whack. Like now, there's different registers that cannot be out of whack during execution, but RSP is just very importantly always pointing to the top of the stack and to the manages the stack frame. That said, RSP, like the virtual value of RSP, can also be used for defining where a function starts and ends. Simply spoken, because RSP manages the stack frame of a function, it is inherently attached to the function, which is how function detection knows to leverage it to define like where a function starts and ends. Without that function start and end, we can look at that quickly in the text view. If you press the space bar, you change to the text view, which would look approximately like this. You can see there's a sub proc near subroutine. So IDAPRO detected that like at this address, 14,050, we start a subroutine. And at the same time, magically, it has detected that there is an endpoint. So here is where sub 14,1050 ends. This is all being done with calculating the stack pointer. If IDAPRO cannot do this, if something looks messed up in the level of like in the stack frame format, or like I'm not necessarily talking cryptors and packers here, but sometimes a weird compiler setting can throw the disassembly framework off. And then, in fact, this function detection feature is rather easily thrown off. I've seen lots of examples where GCC compiled binaries will not compute well in IDAPRO's function detection. And yeah, typically developers are very quick in fixing this, but I suspect if a new GCC comes out and you throw in all the optimizations that GCC has, that most disassembly frameworks will have trouble, at least in the beginning, to detect functions and spit out proper disassembly. That's just the nature of how binaries look like. Yeah, and if like in the IDAPRO case, if IDA cannot find the functions, then pressing the spacebar and jumping back to graph view is not possible. Now, the graph view. How the blocks are typically found is by following the call graph or following the flow of a function. You see there's a jump instruction, and the jump instruction has two possible outcomes. If the jump is taken, we go to this address. If the jump is not taken, we continue the code flow. Let me quickly show you in the text view. Where is the jump? Here's the jump. So this is the jump instruction, right? If it is taken, we jump to this address. If it is not taken, we continue execution as from where we came from. So we continue to the scroll instruction. If the jump is not taken, we just go down the line. And another case, down here, for example, you see a non-conditional jump, just JMP. Doesn't wait for a condition, will jump to this address in any case. So there's no way we're going to continue this execution on here. Again, jump instructions and conditional jumps and negative conditional jumps, now that can be very confusing. And in the beginning, I would really just recommend you suck it up and read through the code and try to logically conclude which jumps will be taken where and what not. Spacebar and we come back. All right, now my focus is on this one jump instruction. I told you this will always be taken, and the graph actually explains that for us already, and we don't have to look up the documentation of this jump, because just by looking at the graph view, we already know that this jump is like a one-way street, like this is always going to be taken no matter what. And in fact, I think especially for beginners, this graph is essential. Like if your tool cannot give you this graph, then your start into the reverse engineering sphere is just going to be so much harder. But yeah, that's my personal opinion too. If you want to start reverse engineering on object dump output, go ahead and be happy. It's perfectly well possible. For us here, we keep looking at the clicky graph. I'll have a sip of my coffee. In the end, how IDAPRO knows where exactly the blocks are and how they fit together is again following the flow. These two blocks are only two blocks because this loop arrow is coming in here, because this block here has this block up here as a destination. If you look closely, you see there's a non-conditional jump going to that address. If you look at this block down here, there is no jump that takes us to this block up here. So what's actually happening is that this block and this block in the code are adjacent. They're like this block follows this block. And either Pro has seen that this jump up here also terminates in this block, so it took this piece of code and flipped it around and put it on top of this bigger bubble of function that we see in here. That said, it can be very confusing comparing the text output and the graph output because they don't typically align. Like either Pro will pluck this graph together how it sees fit, and frankly, different tools show you different graphs. So if you look at the Gira graph output of this, it will very likely look a little different. That's the nature of things. Okay. Did that answer the question? I see people in the chat are explaining as well. Very good. Is there any other questions so far? Or any questions that need me anyway? I didn't think so. Awesome. Once again, a big thank you to the moderators and other people in the chat who help explaining and answer questions. That's great. Like my focus isn't usually on the streaming window, so I don't actually follow the chat. But I have so many helpers in there. That's awesome. Okay, what did we want to do in here? We wanted to analyze the code flow. So again, at the first look, we see there is an interesting branch up here. We see there is a big loop that loops around here, and we see a switch case statement that's down here. And we want to go analyzing these three. First, that condition. Oh, at first, something I haven't actually talked about yet. At first, we can see in the first block, there's a string, which is such a string much well. Well, here, this is the address of the string, not the actual name. Remember, this is an address, and IDOPRO tells us what is located at this address, and based on what is there, IDOPRO decided to name this address constant. By the way, a constant is also just an address. If we had an integer constant defined in our code, it would show up as an address in the code as well. As it is IDOPRO, we can double click on everything. We get to the actual strings in here, and we see other strings as well. Or you see the ones we looked at in the last class. Okay, anyway, enough about that. One more thing now, there is views in here. This view exists in most reverse engineering tools. There is a strings window. If you open view, open subviews, there's a whole menu where you can pick subviews from. And there's something in there called strings. If you open that strings tab, IDOPRO spits out everything it found in the binary that looks like a string. With looking like a string, we're talking about, I think, 4 or more consecutive ASCII characters. So remember, ASCII characters have like numbers, like hex values, and ASCII is defined as a range. So everything that falls, like every byte that falls in this range of ASCII character IDs, so to say, like the hex representations, is detected as a character. And if the string detection IDA finds something that's 4 or more ASCII characters, it puts it in the string list. In our case, it's nice and clean because this is a very small, clean binary, but in a big binary, the strings window will show you a lot of content with a lot of garbage. Just be prepared for that. We actually have to speed up so we can look at SQLite. Okay, that's much about the strings. And then you can see a call to stringlen. So there's a string, there's a call to stringlen, and then there's a compare of our AX. Now think about it for a second. What do you believe is happening here? And again, I'm not asking you to read all the instructions. Just from a quick sniff, you see there's a string, there's a call to stringlen, and a comparison of REX. If you think about it for a second, you will find out that we're checking the string length of this string that shows up in the code. And then we're checking whether this string length, like the length of this particular string that we measured, is longer or shorter than 15. Again, you can change the representation of numeric values by right-click and then picking one of the options that's down in the menu that you cannot see right now on my screen. And we pick the decimal representation and tells us 15. So we try to find out whether our string is longer or shorter than 15 characters. And if I'm counting here, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, it is definitely longer than 15 characters. Oops, that was a double click, sorry. It's definitely longer than 15 characters. We have a JNB, which stands for jump not below. And if you were a good reverse engineer now, you would look up the flag conditions that would trigger a JNB jump. Or you look at the code flow and you conclude that we're checking the string length and we want to see is our string bigger or smaller than that. And if it's JNB, we could say that if it's smaller than 15, we do not take the jump, and if it's bigger than 15, we do take the jump. Again, by looking at the bigger graph, you see that a negative decision would take us down here. If we have a quick look, what you find in there is XOR EAX EAX. That effectively sets EAX to 0. Like if you XOR a value with itself, you zero it out. And after this instruction, essentially our EAX register is 0. The RAX register, actually. And after that, there's just a jump. Then we clean up the stack frame with an add RSP48. This cleans away the stack frame, and then we return. So you see, if this jump is not taken, like if we do not take the screen branch, but we go down the red branch, all that happens is that we return 0. Remember, REX is our return register. So if you set that to 0 and then return, what you do is a return 0. Okay. So if the string that we see in here is shorter than 15 characters, we return 0. Yay, we analyze our first branch. And if it's bigger than 15, we follow the screen arrow. Okay, then we set on these two basic blocks. There's another called a string length coming up down there. We set some variable to 0 and we have a non-conditional jump. A quick talk about variables. Occasionally you see a lot of variables used in a piece of code, especially if there is no optimization happening. You might see a lot of different variables being used where technically if you would write the code yourself in, like say you write C, you don't use 25 variables to juggle 3 values around. That's not what the coder does. Binaries sometimes do that because again, the way compilers work is they just translate piece by piece inside of C code. If there's like a long C code statement, the first thing the compiler does is split it up into different statements. So if you have a very sophisticated long arithmetic statement where you multiply and add different things, and the compiler goes along and says this is too much for me and spits it up, splits it up into different smaller parts. And then each and every of these small parts is translated into binary. If you don't use optimization, this is very literal, like every piece of code results in a given pattern in the binary. And then we get like very large, very not complex, but say overly enthusiastic pieces of binary code that for us humans seem very, very stupid. But again, I like to turn optimization off in exercise binaries. Quick look up here. If you get to the entry point of the function, you see that variable 28 exists here, and it's a dword pointer. What I did not talk about before is there's a variable 24 and it's set to 0 in the beginning. We don't know yet what either variable 24 or 28 are used for, but we know that both of them are being set to 0. So you can go ahead. So either you take a mental note about this. This is a small function. We can survive with mental notes. Or you take a piece of paper and really go take notes on a piece of paper. If you look at a very large function, you will want pen and paper to be able to keep track of the control flow and like the different variables and how they change. It would be alluring to just call this variable set to 0. So much later when you go through this function and you see it used again, you know that it has the value 0. But something to remember always is that variables can change values, and naming a variable after its value is just not a good idea. So before actually assigning a name to that variable, make sure you get a grasp on what the purpose of this variable will be. Anyhow, we have this mental note now. 24 and 28 are set to 0. Then, as we move on, there's another call to string len, which means we know the argument that's handed over to string len is going to be a string pointer. IDA knows that too, which is why it auto-renamed that variable here. What else is interesting in here? Here's variable 28 again, and variable 28 is loaded into variable 10. Interesting. So variable 28 is set to 0, which means that variable 10 right here is 0, 2. And so 0 is loaded into RCX and compared to RAX, which means that we're checking the string length of the string pointer that came in and see whether it is 0 or not. Now, hold on to your brain cells. So here's a loop, right? Well, loops are basically built on data that changes. If you imagine a loop in a C file, there is usually a counter. The counter either counts down or counts up, ideally, and there's usually something being modified in the loop. Like if you're not having an empty loop, something happens in there. Like data is stored somewhere, data is loaded from somewhere, data is loaded and modified and stored somewhere. So either of these activities usually happen in a loop. All right, we'll move on from here by looking where our loop goes to, which is curious. So this branch down here is interesting. Again, loops usually have exit conditions. What is interesting for us is how's the state of execution when we enter the loop? What makes the loop go around? Like, why would we exit the loop? If you look at the graph, you can see that this green branch will be the exit. Like if we hit this green branch and if we hit the next green branch from here, we get to this one basic block down there where we have another XOR EAX, EAX. This is another return 0. So, I'm sorry, by the way, I'm surfing through this graph so quickly. You're very welcome to watch the video afterwards again and see what I'm talking about. Yeah, but we're really in a hurry. So again, we have this entry block that enters our loop. We know it's the entry block because the loop arrow terminates in here. We see that there is a very short path to return 0, which means if this first condition is true, we jump down here, and in there is another condition where we either walk on to the switch statement or we exit with a return 0. Something that's very interesting in the beginning when analyzing a function, by the way, is starting at the bottom and seeing what's the possibilities for exit. So here's the return. There's only one return in this function. There might be more than one, but this one only has one. And in there, we see that there's 3 possible results in this function. 2 of them are returning 0, like XOR, EAX, EAX, and one of them is returning 1. Ideally, if we're interested in what gives us a positive outcome of the function, we look from here up to see like what can trigger this basic block to be executed. Okay. Whatever though, we want to know what the loop does. If you look at the graph, and it looks a little confusing because the switch statement is right in the middle of this whole function graph, but the switch statement actually doesn't have anything to do with the loop. If you look at this, like if we want to exit, we go down here, like this branch already means that we're exiting the loop. And if not, we walk on over here and from here down these basic blocks to eventually loop back around with this basic block down here. Okay, so what we want to analyze is this stash of basic blocks over here on the right side. These three and the one that makes us loop back around down there. Okay, let's maybe start in the middle. Is our string length stashed somewhere? No. So there is a string pointer that you saw in the first block up here. Let's just quickly look at that again. We look at the string length of that string pointer and we compare it with 0 in the first iteration. We cannot be sure that variable 10 will remain 0. Again, that depends on variable 28. If you look, 28 is loaded into REX. REX is stashed into variable 10. Variable 10 is loaded into RCX after the function call. If we were using optimization, this would look a lot simpler. But yeah, sadly, we have to bear with this right now. So RCX at this point in time, like at the first iteration, when we hit the function for the first time, is 0. We would be interested in where the string pointer, this pointer here is pointing to, and how variable 28 will change in the course of execution. And for that, we can have a look at all the blocks we just identified a part of our loop. And the one important one for this will be down here. Let's have a quick look at this. There's only 3 instructions, right? So variable 28, remember that was set to 0 at the beginning of the loop, is loaded into EAX, and then we have an inc instruction. Inc increments the value in the register. So after this instruction, EAX holds 1, and then that is stored back into variable 28. This is essentially the I++ in your for loop. So you have for I equals 0 /dot I++. Now, the first condition, I smaller given value, like I smaller string length, for example, and then /dot I++. So this plus is what you see in these 3 instructions down here. This is where we increment the counter. Deep breath. Okay, we just found our loop counter. Now we can go ahead and rename the variable because finally we found the purpose. You click N and type in loop counter. Enter. Awesome. By the way, variables totally can have multiple purposes in a function. So sometimes it's confusing because you have a big function and there's a loop in the beginning and first the variable is used as a loop counter. And then somehow, it's bad practice, but developers reuse variables and later on the same variable is storing some other integer value that the developer decided to put in there. And then the purpose of the variable changes. So we might have renamed it loop counter, but it might still happen that later in the binary it is used as a totally different thing, which is sometimes confusing. Anyhow, for us right now, let's go back to where we came from. The top box. Yeah. So loop counter is set to 0. Loop counter is loaded to REX, ends up in variable 10, is used for a compare. It's the loop counter. It's not necessarily 0. And REX is the string length of the string, and the string might change too. Anyhow, by now we know that this RCX here is representing the loop counter. So this is first 0, then 1, then 2, then 3, then 4, then 5. And how far do we go? That is a good question. Let's move on a bit. What's interesting now is where the string comes from. Now, if you see a variable being used in the binary that hasn't been initialized yet, you can put the focus on it and zoom out and look for yellow highlighting. I think that's a dirty trick. I'm not sure that's a good reverse engineering practice, but that's what I usually do. So you scroll out, you see there is more highlighting in the first box, and we haven't analyzed that yet. bad. What we see in there is the string variable. So this is a quad word pointer, like a usual 64-bit pointer, and it holds the address of our constant string. Surprise, surprise. Okay. Now that we know that, the box down here makes more sense. You see what I mean? Like usually reverse engineering isn't like you start at one instruction, go to the bottom. You can't do that. But usually what it is for me is you zigzag around a lot in the graph. Like visually you identify where the interesting stuff is. And from there you go finding all the bits and pieces that go into the interesting stuff. And that might not, it's what I do. It's my dirty tricks. It's maybe not what other reverse engineers would tell you to do. But anyhow, I'm a dirty trickster. Um, From there, we now know this is our constant string, and we fetch the string length of this string, and then we check for where our counter is at. So we have a counter starting at 0, and we want to exit that loop, like we want to take this jump when our counter is equal to the string length of that string. Quick recap. We have a string, we have a counter, we start at the first character, like 0 is the offset of the first character. We increment it by 1 with each loop, which means we might be using the counter to walk from one character to the next, to the next, to the next, to the next. Characters are 1 byte big. So by incrementing this pointer by 1, we get exactly the next byte, next byte, next byte, next byte. And this way we can loop through the string. Now let's see whether this is actually what's happening. This string pointer is going to be very interesting for us. Go down here. Indeed, next box, we see there is a loop counter, which is loaded into REX. We see the string pointer, which is loaded into RCX. We see a move with sign extension that loads a byte. You see that here, only a byte from a location, which is indicated by RCX plus RAX. So we take the string pointer, we add the loop counter, and visualize the string in front of you. You have this constant string, which has different characters. If we have the pointer that points to the string plus the loop counter, we always get exactly the one character that's pointed to. This way, in this loop, we go from character to character. If this is all a bit much, feel free to go ahead and take comments or like take notes inside of either Pro. So for example, we could go here and with the double dots, we get the comment window. What would be a good comment? We are iterating a, a string. I suck in naming, I suck in commenting, I suck in taking notes, I'll be honest. Anyhow, we're iterating a string in here. So EAX, after this operation here is done, will hold a character. The SX tells the CPU to extend this byte that we load in here with zeros, so or with zeros or ones, depending on whether it's signed or not, sorry. And characters are typically not signed. So the upper bytes of EAX that are not filled by the byte will be zeroed. And this is important because the next instruction is a compare, and we compare with a constant. So here's a byte constant that we want to see in the lower byte of EAX. And for us now, it will be interesting what that is. So you can conclude we're iterating a string. Again, we analyze that here. And we're comparing a character that we loaded from the string with a constant. Now we're in here, and again, we can change the representation. Now we could go and change this to a decimal representation, which is 95, which isn't exactly helpful. Again, we're looking for a character. And IDA offers us to display in different representations, and it's neither octal nor binary, but it's a character. So the last option we have here for display is what we pick, and it shows you a character. More importantly, it shows us an underscore. Now you might be remembering this whole stash. This is a piece of code that we actually looked at, I think in the second class that we did. We were iterating a string, we're looking for underscores, and what you will find in the next basic block is that we try to count those. So compare EAX, the character we loaded with an underscore, conditional jump. We could go again and check the if flags to see what a J and C based on a compare instruction would do. The compare instruction sets flags in the if flags, and J and C checks those flags. This is how the CPU thinks. We as analysts can go and see we're looking for an underscore. If we find the underscore, we take a certain action. If we do not find the underscore, we skip that certain action and land in the basic block down here. What do we do if we find an underscore? We load variable 24 into EAX. We increment variable 24, and we stash the incremented value back into variable 24. Now 24 is still in our memory or on our notepad if we take notes on paper. And variable 24 was initialized with 0 in the very first basic block. To show you this, I can use this little graph view down here and just click on the uppermost box in the graph, which takes me back to the entry point where we see variable 24 is initialized with 0. Clicking back to where we came from, which was this tiny basic block down here, where we see variable 24 is incremented by 1 every time we find an underscore. This tells us that variable 24 effectively is the count of underscores in the input string, in the string that we handed the loop. So we go ahead and rename again. Underscore count. Horrible at naming. Underscore count. Okay. We can conclude that if we hit the end of the string, in this box down here, if our loop counter is hitting the end of the string, like this is a value, but this is a pointer, right? And essentially what what we're trying to do is we're trying to avoid to point outside of the string. So if the counter is bigger than the string length of the string that we're evaluating, we want to exit the loop in order to avoid exiting, like in order to avoid not to overcount the characters, like operate on memory that's not actually belonging to the string. That's essentially what happens. And yeah, once we hit the end of the string, we know how many underscores are located in the string we're looking at. Okay, zooming out again to show you the whole loop body, which is analyzed. We have a loop counter that's incremented in this box down here with each iteration through this flow. And over here we have the loop body where we're looking for underscores in the string and we're counting how many underscores we found. So we know by the time we hit this range, by the time we're at the end of the string and we exit over here, we know the number of underscores. Now, since we gladly renamed the underscore count variable, we know that right after we exit in this basic block here, right after we exit, we see that this value is loaded into EAX and from there ends up in the variable 20. And from there is compared with 5. And there, IDAPRO gladly already told us that there is a switch case coming up. Then, what's important in this block is we have a jump if above. If the value that we counted is above 5, so if we counted more than 5 underscores, we take this jump that takes us out the left side of the screen. If it's smaller than 5, I have to watch out I'm not telling you bullshit right now. I believe if it's smaller than 5, we take the branch to the left side. Once again, I'm looking at the jump instruction. I do make assumptions based on the code flow. I didn't actually think in detail about which flags are being set by compare and which flags are being checked by jump if above and so on and so forth. I'm not saying this is not what you should do. Like if you really want to understand the code flow and if it's not obvious from the logic of like which direction is going to be taken, then please, please, please take a cheat sheet with the flags and go analyze in detail about how exactly jumps work. I'm usually too lazy to do that. But from the code flow, we can see that like if our value is bigger than 5, we take one way, and if it's smaller than 5, we take the other way. Let's have a quick look about the exit. So, whoops. Oh, by the way, you can also double click on arrows and jump back and forth between boxes, which is a very neat feature if you look at the big graph. So this this one arrow takes us to a return 0. So you can see if this compare instruction tells us that our value is bigger than 6, we return 0. And IDPro here said that that's the default case of the jump table. So this box is still part of the jump table. Okay. What though happens if not? So in the other case, we walk into this beautiful box, which is usually how a switch case is implemented in assembly, where we see our value. Variable 20 contains the count of underscores. It's loaded into our AX. We load the offset of our code segment into RCX. We haven't talked about code segments at all. I'll spare you that right now. If you want to look it up, like look up the segmentation on that won't help you much. No, don't look up segmentation until forget that the CS is there. It's not very helpful by reading in reading binary. So we load this address, this big address, which is the beginning of our executable portion of memory into LAA. It's an address into RCX, sorry. And then RCX is added the counter times 4. Wait, what? Oh, so this is a pointer which actually takes us to an offset inside of the code section. And from there, we try to figure out the address of where we want to execute. So the counter is our index into these pieces of code. You see every basic block has an address. There's different addresses. And what we're trying to find out is the address that belongs to our case. So if we have the case 2, for example, our AX in this case will be 2. And we, like every time you see something multiplied by 4, this is fanned out into a bigger memory range, into a bigger range of bytes. So you have the RCX, which is the code segment, plus the score count times 4, and that all subtracted from the offset where we are is eventually going to take us to the offset down there. Yeah, it's a bigger piece of math. I don't actually want to think about this in detail now. As a homework, you can try to figure out what exactly is happening in this line of code. I can promise you though, once we add the code segment, yeah, we subtracted it here, so we add it back again. Once we add that address to the result of this operation, we eventually jump, like REX will contain the address of the basic block of our particular case. So based on which number rolls in the REX, we then take a jump to the specific case's basic block. That can be Oops, where's my control here? By the way, scrolling in and out works with the scroll on your mouse and pressing Control, and you can change the size of what you're looking at. And the number of cases we're looking at are 6. 0, 1, 2, 3, 4, or 5. So we can conclude, if we find 0 underscores in our string input, we end up in this box. If we find 1, we end up in this box. If we find 2, we end up in this box, and so on and so forth. And if you look at one particular box and then compare it to the others, you see they all do the same thing, like almost. They load a string argument into RCX and then call printf. And if we quickly look through all of these, we see they all do the same thing. So like there's different string constants, to be sure, but each and every box tries to print some output. And now if we double click at one of those, then we are taken to the data section again in our binary, where we see all the different strings in a list. That's more convenient than looking up each and every one of them. So you could see that in the first case, if we find 0 underscores, we get to the string boring. If we find 1, we say we found 1. If we found 2, we say we found 2. For 3, we say we found 3, and so on and so forth until we found 5. Okay, so these are the different strings that are possibly printed based on the number of underscores we found in the input string. Ooh, that was exciting. And after either of these basic blocks happened, they all end up in the return 1 basic block. So all of these arrows that are highlighted here right now, all of these arrows come out of the jump table blocks. So if we successfully iterated through the string and found the number of underscores and went through the switch case and printed a statement based on how many underscores we found, we eventually end up in this basic block and return 1. Because Rx is initialized with 1, and then we go clean up the stack and return. Wow, that was exciting. Now, bigger picture, what does this function do? It gets a string. It checks whether the string is longer or shorter than 15 characters. If it is longer, we go on a hunting spree and we look for underscores. If we find underscores in there, if we find anywhere between 0 and 5 underscores in the string, we print a statement about how many underscores we found and exit with 1. If we found more than 5 underscores, we return 0 and exit as well. All right, that was it. That was the exercise binary and the last exercise in there. Now we can move on to SQLite. First of all, though, are there any questions? Let me look at the chat. Oh, yeah, interesting. The compiler found out that the value in the calculation will not exceed the 32-bit value and therefore uses EAX and saves the prefix for the 64-bit instruction, resulting in smaller code. Very nice, thank you. Yeah, that's probably what happens. Compiler optimization is nasty. Looking at the width and the length of registers isn't usually something I spend a lot of time on either, especially if trying to get to the bigger picture of a function. Granted, sometimes you miss details if you don't look at all the details. Like register width matters, don't get me wrong, it is important. But usually what I do is I go through functions in a sweep. Like I try to figure out the bigger picture and from there work out the smaller picture. And I'm talking about this a lot Well, you see, it does actually matter for us, like what the sizes of variables are, for example. Um, you will see when we look at SQLite, at the SQLite DLL, though, that you do not actually want to analyze each and every function and each and every code block in details. That is something that is just too painful because bigger binaries have just too many functions and too much code going on. Then there, again, it is important to find the important pieces, the ones that are interesting for us as analysts, and continue your work from there. And we'll see in a bit how that looks like. In the switch case, how does the compiler know the address of each case destination? Here, each case has the same number of commands. If a case has less or more commands, how is working regarding the address? So the compiler is God. Okay, so the compiler knows, the compiler is the one who defines the addresses. The length of a basic block does not matter in this code offset calculation. And in this case, the compiler might have done an assumption about the length because the compiler knows how big each basic block is. The compiler is the one creating them. You can see in a bigger switch case that this address calculation might or might not be somewhat more complicated, or the compiler might or might not decide that there is no address calculation happening whatsoever because it's faster and smaller and more convenient to just build a number of jumps. Something I haven't mentioned overall when looking at these graphs is not every switch case looks this pretty. Not every switch case results in this regular stash of blocks. And sometimes the compiler takes a switch case in the code and spits out a number of compare instructions and jumps. And that depends on how effective the output assembly would be. Compilers do ridiculous mathematics around trying to figure out how to generate less instructions and how to generate faster instructions. Yeah. I might have missed it, but you keep saying basic block. Is there a non-basic block? I don't think so. That is a very philosophical question. I'm not sure about the history, but I think the concept of basic blocks came up in binary analysis. Oh no, actually compilers also talk about basic blocks. A binary is a graph. Um, a, an application is a graph. Your C code, if you wanna write an application, is a graph. You have the entry point of a function, then you have code that executes, then you have a branch, then you have two possibly parallel strains of code that could execute in either or fashion. Then you have a switch case where you have 5 different pieces of code that could execute. So you see you have this tree structure, and if you look at your C code, there's already basic blocks in there. Like there's blocks. We call them basic blocks because they're the most basic block in the code. I assume if you take a number of basic blocks, then you have something that's still a block, but not basic anymore. Yeah, this is really a matter of naming, I guess. The term basic block is just really very common in binary analysis. Like, if you can detect basic blocks, you can eventually detect functions. If you can detect functions, you can build a graph. If you can build a graph, you can do so much more analysis than if you just look at the text representation. Yeah, so that's why I really, really love basic blocks. But as you mentioned, GCC also talks about basic blocks, so I guess it's just a universal term in the binary world. Is there something else? You're welcome. Yeah. There's odd behavior of x86 that if you load EAX, the upper bits of REX get set to 0. That is true. You can spend hours and hours reading the Intel documentation to figure out which instruction has which side effects. And that little side effect is not documented enough, honestly. It is very curious. But yeah, um, if you go reading a piece of code instruction by instruction, I would really recommend you spend some time on reading the official manual, like the official documentation for each instruction, just to get a feel of like how Intel CPUs see instructions. It will make you think about binaries a lot differently. It also takes a lot of time, so don't worry if you're short on time, but it's a very interesting exercise. All right, we're done with the first binary, part A, and now we're gonna move on to the big thing. Now we're gonna see the actual real code. And therefore, I would ask you pick the SQLite3 DLL from the folder where you stashed the exercises, which is something I have to find now too, because I don't actually remember where I stored them on my drive. And we will want to open the SQLite3.dll and load it into IDA Pro. And you have some minutes to do so, because I literally forgot where I put them. Oh, there they are. Okay. So, and IDA it works beautifully if you just drag and drop another binary in there. Then IDA asks you, do you want to pack the database? Something I mentioned at some point is that IDA's view of a binary is a database. If you load a binary in there, the analysis runs and generates a database. And when you close a binary, IDA stores its database into an idapro.db file. That is important to know because, like, if you work on this database, like you modify something inside of IDA Pro, you're just changing the database. You're not actually changing the binary on disk. That is something to keep in mind. Click OK. I just remembered that we wanted to debug. We haven't actually debugged anything yet. And we're short on time. Let's dig a bit through SQLite, and then at the end of the session, we're gonna fire up the debuggers and you get to debug the exercise binary. Okay, so I dropped SQLite in there. I clicked OK on the default analysis settings because we're still looking at the Windows PE file. And then I sit there and wait. Don't click anything in the beginning. First, when you load a big binary into IDA, it needs time to actually analyze. And that could take up to a couple minutes with this big binary. Yeah, if you take an even much bigger one or a much more complicated one, this could very well take a couple minutes to actually finish. And you see when it's finished, when actually the bar, this colorful bar at the top of the window shows you the progress of the analysis. There's like a little arrow that windows up and down. That's the different analysis stages that IDAPRO executes. And then let's just for a second appreciate the beautiful function list that you see on the left side, where there is an endless ocean of functions. Some have names, some don't, some are library functions, some are imports, and all of them are a lot. It's 3,197 functions that IDAPRO found in this binary. Cheers to that. Now, what are you planning to do in here? You can see from the sheer number of functions that it is very unlikely that anyone ever reverse engineered the whole binary of SQLite3.dll. Once again, for this binary, I did not use any optimization. And if you don't optimize, you very likely end up with a lot more functions than if you use an optimizer. That be said, but even if we would turn on optimization full force, we would still see a big number of functions in here. You lost my voice. That sucks. Am I back? Can you hear me? Which debugger will we be using? We'll use the built-in IDA Pro debugger just because we're lazy. and because it functions so well, clicky, clicky. Yeah. Okay. Interesting. My voice was gone for a few seconds. Apologies. Yeah, I'm not really happy with this mic. It keeps moving. If I keep my head pushing my head forward, it slides, and then the mic slides with it. And I guess when it touches my face, then sound goes to shits. Apologies. Okay, Escalate 3.dll with a very beautiful view on the DLL main function, which does nothing but return 1. What's DLL main? What's a DLL? Um, so Windows has different forms of executable files, which is sys files that are drivers. They're all portable executables, but there's sys, which is the kernel subsystem. Then there's a Windows PE, which is a regular .exe. You can double click an exe and it will execute, show you all it has. And then there's libraries, .dlls. And DLLs you cannot double click. Remember, you can't just double click a DLL and it will execute. That is because it expects to be loaded. A DLL wants to be loaded in the context of another binary, in the context of a process. So if you load Microsoft Word.exe, Word loads into memory and loads libraries that it needs for execution. Most importantly, for example, kernel32.dll. That is a DLL that most Windows executables require for executing. And kernel32.dll is a library. It wants to be executed in the context of a process. You cannot just execute a standalone DLL. There's tools that help you load a DLL if you want to analyze it dynamically, but you can't just double click it. You can just load it in a debugger and expect it to run. The purpose of a DLL is to expose functionality. So you still have one main entry point and you still have DLL main, which will execute when we load the library. But the main purpose of it is to expose functionality, like to export APIs, if you want to put it that way. So you export functions for other executables to call. We can see those exposed functions if we look at the export table. Remember in IDA Pro, we have these different views, the hex views and the imports and exports are the ones that are interesting for us today. And let's have a quick look at the export table, since I've been talking so much about it. If you look at the regular executable, you have one export. That's your entry point. That's your one address that will be executed when you load the binary. A DLL typically exports a number of functions. And if you look at a grown-up DLL like SQLite, you see that there's a lot of exports in there. These are a lot of exports. If you disassemble a Windows DLL, like you throw kernel32 in here, you see a much longer list. You see like a lot of functions that are exported. Okay, now for us that means, first of all, the names of these functions are known because they're stored in the export table. The export table itself holds the names of functions that are being exported. You can see that in the CFF Explorer. If you load this very same binary into CFF Explorer, and there you see the export table as well, and you see the very table. Like this is a neat and cleaned up version of the export table. In CFF you see a little bit more detail. Anyhow, for us it's just neat because for lots of these functions, we know they have a name, and from the name we can derive of like approximately what they do. And if we want to know in detail, we can look up documentation. Typically, libraries are more or less documented, and I see typically it's like there is malware that comes in the form of libraries, like malicious code can do that, and they don't usually come with documentation, so forget what I just said. But if you look at an official DLL like SQLite, you can assume that the functions that are exported from SQLite have documentation. If we were super lazy reverse engineers, we would just go and look up the documentation for these functions, and we wouldn't have to reverse engineer anything at all. That would be boring though, since we're in a reverse engineering class, we won't do that. Before we start into any of these functions, yeah, just a quick look at the first window again. Here's the DLL main. And for all I know, the DLL main is always executed when a library is loaded. So this is something that will always happen. And that's typically a space where you can stash activity that your library needs to be able to execute properly. Like this is setup and initializing code. And yeah, again, this is always executed. And the exports are typically just executed if someone calls them. So if the process that loaded our library calls this particular export, then it is executed. Otherwise, it's not. Otherwise, the DLL is loaded into memory and it just sits there and waits to be interacted with. And by the way, each of these exports can also call another export. So for the binary itself, they're just regular functions. They're code that is located inside of the big code section of our binary, and one of these can call the other, and so on and so forth. So that is a possibility. Now, before we actually look at the code, have a quick look at the imports and at the strings table. So first of all, the imports are a lot bigger, like there's a lot more of them in here than in our little exercise binary. And here we count 118, and if you load a browser binary, if you load firefox.exe in here, you'll see a lot more of these. And the other thing I wanted to show you is how a serious string table looks like. So if we click on strings, we see a lot of stuff that either Pro identified as strings, which isn't necessarily readable strings. Like lots of these actually are. If we scroll down and down and down and down, where's the readable strings? Damn it, I'm looking for a non-readable string. Oh, okay. Anyway, so if you scroll to the very bottom, there is some garbage lying around. So these here are readable characters. There's a C and a question mark and an A and a large U and a large Y. So for IdaPro, this is string. For us, we see this is not actually a string constant. It's garbage. It's bytes that happen to be in a range of ASCII characters and in a continuous chain, and IdaPro thinks it's a readable string and it's not. So in that sense, looking at the strings of a binary, especially if you look at malware, might be interesting, but don't trust everything that you read in there. Like if we look at this percent dot star s, we know that this is something that could happen in, like this is a string that could appear in a binary. But for IdaPro, this is just another chain of ASCII characters and might or might not actually be useful for an analyst. If you go through this, you see a lot of strings. And say you were looking for particular activity, like you were trying to figure out where SQLite flushes databases caches, and you wouldn't know where to start. Well, first of all, you would look in the documentation whether there's any APIs that do exactly that take you there. Or then you could go and look for anything that you could look for a string that indicates any such functionality. And I'm not after this particular one, but just to show you right now. I was curious. There's a string that says materialize %u. So SQLite wants to materialize something. If we would say this is an interesting bit that we want to look at, we could double click on the string in here. We're taking the strings table, and from there we can click X, and X shows us the cross references. Oh, and interestingly, this materialize string only has one cross reference. And if I double click on that, I see a function that uses this particular string. And if I were in any way interested in what materializing does, I could start right from this basic block and see what happens in there and work my way out to see the bigger picture, like to see the bigger function, the bigger piece of code that we're looking at in here. And that might be quick or it might take days. If I scroll out here on this one random function, you see that this is a big function. In reality, it's probably not. Like for the SQLite code base, this is probably an average size function. But for us in the disassembler, it looks horrific, horrible, horrific too, horrific as well. You see with the basic analysis approach I told you before, look for the branches, look for the switch cases, look for the loops. We're stuck very quickly because there's just so much code in front of us. But what we can still do is we can still see that there is this one condition, like two conditions up here that take us all the way to the exit. So again, there's something happening in the beginning which causes us to return one right from the start. You see that here in this one basic block, there's three blocks then here, and we return one on each of those, which is an interesting piece of information, which if I wanted to analyze this function, I would go ahead and write it down on a piece of paper. I'd be interested in where do these two come from right here, and what the two conditions are. Like here's a compare and here's a test. What are these conditions that cause our function to return for one right from the start? And from there, you could go and like look at different other things that might be interesting. Like here's the first loop. If there is a loop, there's something happening in the loop, which are probably these three basic blocks right here that perform the interesting action, and so on and so forth. And there's other loops, and you can go work with hypotheses and go work with suspicions of what you think is happening in here. And from there, go analyze in more detail, which we won't do right now. I just wanted you to see how a real life function can look like. And you can imagine that you can spend hours and hours and possibly days and weeks on analyzing such a stash if the code is really complicated and you really need to analyze it in detail. Okay, so we have a lot of functions and they have a lot of basic blocks, which would be a lot of work if you would want to analyze in detail what's going on here. So what do we do? Again, a big part of our job is to figure out what is interesting. Like what are we after and what are we looking for? And say I made this up and I looked at the binary before, but today we're interested in string operations. Like how does SQLite handle strings? Therefore, go to the Exports tab and look for string operations with me. And that is easiest done if you scroll down, and it's thankfully all alphabetically sorted, and look for the SQLite 3 underscore str, like this str functions. Can I make that bigger? There's probably an option to make that bigger, but no time to figure that out now. Okay, so we have like a string append. We have a string append all, append char, append the append f, whatever the f is, like an error code, finish, length, new, reset, value, v append f. As you can imagine, we won't go analyzing all of these today. Actually, I don't think we're going analyzing very much of these today at all. Let's do a simple one, string length. This isn't actually a strlen function, but bear with me for a second. So something up front that I find out while looking through here is SQLite doesn't directly work with APIs. It provides wrappers and provides for some activities, it provides its own implementation of certain functionality that you would expect comes from libc or like from our operating system library. That is not that uncommon in large applications. Sometimes the default implementation of certain functionality, like append string, like the str append, as it is called in this binary, isn't suitable for the large application, then developers go about implementing their own. And I bet lots of your developers know this all way better than me. I never actually developed a large application. I reverse engineer them though, which is much more fun. Okay, I'd say let's jump right in. What do we see in export number 209, the SQLite 3 underscore str length? Something that's very boring, actually. Something that gives us an idea that this isn't actually a strlen function. What you see in here is one condition, namely we load the first argument that the function receives into this arg0 variable, and we compare it with 0, which means we check whether our argument that we receive here is 0 or not, and if it is, if it is 0, we do not take this jump and end up here. Again, these conditions are confusing, so we compare these two values. Compare is implemented as a subtraction, so if we subtract one from the other and the result is not 0, the 0 flag is not set. Jump 0 is taken if the 0 flag is set to 1, which happens if the result of this operation is 0. See where I'm coming from? I hate jump instructions. So if they are equal, 0 flag is set, and we take this jump and we land here. So if the input value, like the argument, equals 0, we store a 0 in variable 18. If it is not, we load the argument into our AX. We load a value from an offset, like we assume this is an address, and we add an offset of 18 to that argument and load that into EAX. And then we store that value into variable 18. And then we return that value. So what happens here is that essentially we see how an object is treated. We're not going to go into C++ binaries right now, but imagine you have a struct in a C file. Like structs in C don't look all that different from objects in C++ binaries, really. So like the way they're handled by binary code looks very similar. Imagine that the argument 0 that we get through our RCX here is pointing to a struct. A struct in memory is really just a little block of memory where the different elements of the struct are stored in. So like, imagine it's like this physical block of memory. And if we load a given value from a struct, we just add its offset to the pointer that points to the struct. So you have the struct here and the pointer pointing to the first value. And then if you add 18 hex, you jump down a couple bytes and fetch a value from there. So this move here dereferences REX plus 18, which gives us the string value, the string length essentially. How do we know that we're fetching the string length from, we're fetching a string length from the struct? You look at the function name. So here is a str length. We can totally work with this information. We expect this function to return the length of a string. What we see is the function fetches a value from out of a struct happening here, and this is the value we return. We can work with the hypothesis that this value is the length of a string that might be represented as a structure. This is a little confusing. Think about it for a second. So we have a struct that describes a string, and it stores a value that represents the length of the string. So far, so good. From there, I'd say there is other string functions that can give us more clarity about how the struct looks like and of why it's interesting for us. And therefore, I actually would like to find the export in the function list so I can hop around. Like 300 str, here we are. Okay, so we just looked at the length. Maybe interesting to look at is the str underscore value. That takes us to another function. So in here, we see a similar structure. We see a similar function body where again, you have the first argument, that's the argument 0. We check, is it null? Like, is it empty? And if it is, we return 0. Like, we jump to this basic block down here where we see XOR EAX, EAX, and then return. So if our input pointer in this case is null, we just return. If it's not, we load it into REX and we check offset 18, is it 0? Now we are suspicious. If you remember the string length function before, let's just have a quick look at that again. If I double click this function over here, you see that there is offset 18. Offset 18, we just deducted is the length. By the way, this is a point where you really fetch out a paper, notebook, and a pen and start drafting a struct as you go, trying to figure out what the structure that is our argument here holds. You might want to remember that offset 18 is what we have deducted as the string length. So we now know that 18 identifies the length variable. And as we look at the string value function, we see that we're comparing the same value with 0 in this basic block. How do we know that both arguments are the same struct? Essentially, at this point in time, we don't. If you figure out where these functions are called, and you see that the argument is always the same struct, then you can say for sure that this REX plus 18 and the value that we saw loaded in string length is the same value. A lot of times, reverse engineering in larger applications and larger functions, you have to work with assumptions first that you can go on proving or denying later on. So you would say this is my string length for the time being, and later on when I figure out where the structure is created, like where it is initialized, and I can actually see that the length of a string goes into offset 18, then you can like tick that box and say, I'm sure now that this is not a hypothesis, it's a fact. And this is usually how you go about reverse engineering larger applications. It's just like a lot of hypotheses that you write down, and later on you go about checking and denying and proving. All right, let's move on from here. 3 more minutes in SQLite and we go debugging, I swear. And you can spend a lot of time in your homework in reverse engineering SQLite. What we see come up next, so if our string length is 0, if the pointer is 0 or the string length is 0, we return 0 from the function. If it's not, we go on, we load our argument again. We load offset 18, which we think is a string length, into EAX. We load the argument into RCX again and load another offset from that same structure, from the same piece of memory, from offset 8 into RCX. And then we put a null into that piece of memory when we have the value from offset 8 plus the value from 18. We can assume that this is a string, and plus 18 is where the length of that same string is stored. If we take that string plus its string length and place a null at the end, what we do is we terminate that string, or in other words, we make sure that the string is terminated. Then what we do next is we load that same argument into REX again, and we fetch offset 8 again. You see that there was no optimizer because this is obviously useless because RCX already holds the same value, so we wouldn't need to load it from memory again. Anyway, no optimization here. So we load that string into memory, which we now know is null terminated because we set that null at the end of the string, and then we hit return. So either we return 0 or we return the value of the string structure. You see, we assumed in the beginning we're looking at the string structure, and now as we go analyzing one function after another that has to do with the strings, the picture becomes more colorful. Like we now know where the length is stored, we now know where the actual string value is stored, and we have these two functions that can retrieve either the length or the value of the string. And as you go on looking through these functions, there's like an error code function, which, if I just quickly zoom in, fetches a byte from offset 1C. That could be another piece of the puzzle about how the string structure looks like. And we could say that the error code is stored at the offset plus 1C, and so on and so forth. So by looking through these functions, you put the bigger picture together of how your string object in SQLite3.dll looks like. And the last thing I wanted to show you is the new function. New is where we create the structure. This looks a little more complicated. We will not analyze the malloc function, but we will be interested in this function call down here. And if you just quickly follow me, I'll double click that. You see what a typical structure initialization function looks like. So if we create a new string, like a new SQLite3 string, we land in this function where we have argument 0, which should be our object. Like this is an empty object. It's a pointer to an object which we allocated before. And in here you see lots of values being stored into that object. So rex plus 8 here, rex plus 10 plus 14, rex plus 18 plus 1c and plus 1d. At this point in time, we already know that 18 is the length value, and 1c will be the error code, and plus 8 will be the string that the structure will describe. These are pieces of information that you put together into a bigger puzzle until you get the big picture. As homework for today and for the rest of your life, I'll tell you analyze how SQLite3 deals with strings. It all starts out with this new function, and in there you see how the struct is put together. And once you know how the struct looks like, these helper functions down here, like sur, finish, and append, and reset, and error code, and length and value, these will tell you how SQLite deals with this struct, like what the contents are, how the contents are modified, how they're worked with in the application, and so on and so forth. And yes, homework is to figure out how the string struct looks like and reconstruct it with the help of these helper functions in SQLite3. And by the way, here's like the malloc64. If you click in there, eventually you will find like a hilariously big rat's tail of functions that you might not actually want to analyze. You might just want to believe the function name when it says malloc that it actually allocates memory. And here, yeah, it's really just a very, very big piece of code. All right, this much about SQLite3.dll. I wish we had more time to jump around this code base. It's really interesting. Go at forth and go debugging, no, sorry, not debugging, go analyzing SQLite3 statically in here. There's a lot of interesting functions that you can go about reverse engineering. String compare is interesting. So basically pick a function that you already know what to expect in there and try to prove your expectations by reverse engineering. Okay, this much about SQLite. Any burning questions about this? Yeah. Export names are really stored in the binary, which is helpful if they have useful names. If you look at malware, the exports will almost never have useful names. So in our case here, SQLite beautifully exports named functions. Malware usually doesn't. Malware will actually try to throw you off by naming stuff in a funny way, which is awesome. Okay, anything else? Not right now. Quick. Load the first binary back into IDLEPRO. So we go back to where we stashed those binaries and drop it in there. IDA will pack the database again and will ask us, do we want to load the existing library, the .i64. Here is our database binary, database library. And yes, we say we want to load the existing one. Didn't do very many changes, but what should? Debugging, very quickly. It's not actually hard, it's just a little confusing to look at the different values. To start a debugger in IDA Pro, and we'll be using the built-in debugger. No, yeah, the built-in debugger, because the free version of IDA doesn't actually come with any other interface. That's interesting. Local Windows debugger, that's what we're gonna do. You pick the debugger and then wait, do not actually click the play button already, because the IDA Pro debugger needs a breakpoint somewhere in the code to be called up while executing. Breakpoints are little creatures that tell our CPU to stop executing at a certain point in code. We're not going to go into details there now, but like if you press F2 with your cursor set to one instruction, you get this red line which indicates there's a breakpoint set here. And this breakpoint will tell our debugger to stop executing. This is important because if the debugger doesn't stop, we don't get to inspect the state of the code, which is essentially what the debugger is there for. And we'll be going debugging Hello World right now. You can start the debugger either with your mouse by clicking the play button or with clicking F9. Please read carefully. Yeah, if this was malware, we would not want to execute this on our host system. What just happened? I clicked the play button or F9, sure you feel more comfortable with, and that started the process. That did a lot of things, like a million things just happened. What we did was we started to execute our binary, which means we told the Windows loader to take the virtualbh.exe from disk and to map it into memory. What you see right now, right in front of you, is still IDA Pro's database. What you see here, like all these pretty names and words that you see on the screen, this is all still IDA Pro. But in the back of this, we have a running process in memory. The breakpoint we set here told the CPU to wait for us at this instruction, and then IDA Pro could catch up and actually display the state of the binary. So you see a representation of the binary in front of you, but this is not the actual code. The actual code is displayed down here in this beautiful hex view. So this is our binary in memory as it looks like. One thing, just very quick, click Control S. Control S shows you the segments. This is the segment window. And in there you see, for example, your executable section. This is the text section. You remember this window? Do you actually see that window? No, you don't. That's boring. Anyway, in front of you, if you click Control S, you see the segments. And in there is your text section and every DLL's text section that's been loaded with your executable process. And you see there is a whole stack of DLLs that have been loaded with your running process. And what you see in this window is really your process in memory. This is all of the virtual memory that your executable process can occupy. Okay. What else do we see here? In the right bottom corner, we see the stack view. This is the executable stack where we see our function stack being built up and torn down as we execute one function after another. On the right top corner, we see our registers. And the very corner, we see the eFlags, like status register. We also see modules that have been loaded with our process. That means these are the DLLs that have been loaded alongside our process. And we see threads. Those are not very important for us right now, though. And yeah, in the middle, you see the code as it's being executed. In order to move in a debugger, you use F7 before you click anything. F7 is single stepping, and F8 is stepping over, and F9 is execute. It sucks that these three are located next to each other, because if you don't watch out, you might click the wrong button. Step into, like F7 means that we really execute each and every instruction as it comes along. F8 step over means that we execute the function in front of us without entering calls. That is important. If you see a library function, like you see a call to stringlen, you don't actually want to debug stringlen. Like you don't want to go in there. You can look up the documentation and you don't need to analyze the stringlen function itself, which is why step over is useful. And F9 literally just tells the binary to run, which is boring if you don't have any other breakpoint or any other thing that catches your instruction pointer, because then you would just execute the application in front of you to the end and you wouldn't see what it does necessarily. So with F7, F8, and F9, we can navigate the binary. And let's click F7 a couple times. Watch the stack view in the right bottom corner as it changes, and we just added 38 hacks to the stack pointer and move the stack pointer upwards. And as we click F7 again, we end up inside the hello world function. And the stack just changed. What happened was that the return value, like the instruction following the call instruction where we came from, this address has been pushed to the stack and is now stashed here. For if we hit return later on, that value will be popped into the instruction pointer. Meanwhile, we have a sub RSP in here, then we load our first argument into RCX and call the printf function. Now, follow me with F8. We want to use F8 in here. You click F8, the stack pointer changed again. We allocated 28 hex bytes, hexadecimal 28 bytes on the stack for no reason whatsoever. I think the printf might need it, whatever. And then with the next F8, we load the hello world pointer into RCX. You can now follow in the registers pane on the right side, RCX just changed. It's highlighted in blue. And it now holds the offset of the string, of the hello world string. And then we call printf. And now as you keep on clicking, use F8 and not F7. F7 takes you inside of the printf function, and we don't actually want to debug printf. So we click F8, step over. And then what we should see is there is a little window that came with our debugging process, the debug process, and that says hello world. You can see that again because I would need to create a new window focus in OBS, which I'm not going to do now. You can find that on your pane, on your Windows application pane in the bottom. A new window has been created and it says hello world. So this just happened. Awesome. Then you continue clicking. The stack frame is torn down again. RSP is incremented by 28 hex bytes. So we free memory on the stack. And then we can hit return. You see on the stack view that the bytes that we just freed on the stack, they have not been cleared, they have not been zeroed, which I'm a security engineer. That is a very interesting effect on Intel architecture. If you stash a secret on the stack and your function returns, then that memory still contains the secret if you don't actually zero it. And that is a problem for many developers. Anyhow, another F8 and we're back in the main function. And from there you could go debugging each and every function in there. And that's actually a nice exercise too. Okay, our time's actually already up and I want to tell you about homework. Debug the virtualbh.exe and follow each and everything that happens in the binary, in the registers pane, in the eflags pane, on the stack view, and maybe even on the hex view. Awesome. So we have 2 pieces of homework for the rest of your life, because this is the last class. Debug the exercise binary and reverse engineer SQLite3, SQLite3.dll. Yeah, that should keep you busy for a while. Then this was actually it with our class. And with that, I would say, are there any more questions that I should be talking about? RPH.exe errors out every time I run it. I tried opening it again. Interesting. If I execute this thing to the end, do I get an error? No. I don't get anything either. Huh. Something that could be happening is that the binary doesn't like to be executed in a debugger. So I ran it on a command line without a debugger where it executed fine on my Windows 10. I haven't actually run it inside of a debugger yet. I don't know if that works fine. I didn't test that. What could happen is that your Windows has a different version and some DLLs are mixed up. Like the way I compiled the binary might not be compatible with each and every version of Windows, or like each and every Windows operating system, which should not happen. Like Windows is famous for upwards and downwards compatibility, but that might not always be the case, especially if I compile the binaries. If you can't even make it to the main function breakpoint, then possibly your binary wasn't loaded correctly. Make sure you're working on a Windows 10 operating system and with the latest version of the free IDA Pro. So I couldn't set a breakpoint here. These are issues that I would love to work on in a class where we're all physically together so I could see what your system is actually doing. Win 10 Insider's Preview. I sadly don't know what version of Windows 10 that is and if it comes with a full stack of libraries that are needed for executing. Yeah, it probably has to do something with the operating system. That's the only thing I can think of right now. Oh, the Visual C distribution. Yeah, that's a good point. So you need the C runtime that your executable, like that my executable needs to run. You need the runtime on your system. Running an executable on the system you compile it on is actually rather simple because the system knows exactly what the binary needs, like the compiler figured that out for you. But yeah, compiling a binary so it runs on every other person's Windows is not that easy. I just learned that right now. Are there any other burning questions? Yeah, so this is the last BlackHoodie virtual live stream, but I've been already thinking as we went through here that this was all a bit fast, and I might actually, if I'm bored enough, I might actually do more streams and keep on debugging stuff just because it's fun. I kind of got used to talking to my computer. Isn't that sad? It's starting to be entertaining. Oh, there you go. Someone's missing an MSVCR 110.dll. Sorry about that. I should have added the DLLs with the binary. Yeah, if there's no more burning questions, I'd say this was fun. Thank you all for listening in and for working with me and for asking questions and for being such awesome students. It, I really had a lot of fun. Yeah, I'm mostly thinking about doing one of these streams. Like lockdown's probably gonna go on for a lot more time. And what else would I be doing with my 8 o'clocks in the morning, right? Awesome. Yeah, then I would say that was it. Thanks you all for the attention. And if any more questions come up, please, 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 as always, feel free to send me DMs on Twitter. And yeah, I'll be happy to answer them. And if you want to continue reverse engineering, there's so many binaries out there, you wouldn't even know where to start. You can also ask me for more exercises or for more ideas of like what to continue doing. And yeah, check out the reading materials on the materials page. And yeah, happy reverse engineering. It's a very, very curious hobby to have. It's really, really fun. That said, I wish you all a happy Thursday, and yeah, I hope to see you guys again. If we ever run into each other at the conference, just walk up and say hi. I'd love to actually put faces to the people who listen to this. It'd be awesome. That's it. Goodbye.